Good morning, everybody. I'm Karen Huffman, Pion's Marketing Manager. Thank you so much for joining us for our next seminar. We're going to go ahead and get started. I'm just going to give a few logistics before I introduce Corinne Jankovsky, our presenter. Everyone is going to be on mute, but following the presentation, we will have a Q&A, and Corinne is going to be joined by Boehringer Ingelheim, who is Pion's Technology Manager. Carl Box will also join us, our Chief Scientific Officer for Europe, as well as Naveen Thakral, who's a Senior AD for the Preformulation Group at Boehringer Ingelheim. And although you will have your microphones on mute, you can write your questions throughout the presentation for the Q&A. You're going to see two tabs, a couple tabs on the bottom of your screen, a Q&A tab and a chat tab. I just wanted to ask you if you could please put your questions on the Q&A tab, because after the presentation, I get a written copy of all the questions. So any questions, well, all the questions, including ones we may not have time for, we're gonna do a written document that you will receive with all the questions and all the answers as well. If you do forget and use the chat tab, I'll just send you a quick little message to put it in the Q&A tab. So thank you very much for that. You will get a link to the recording a few days following. It will come through as a Ring Central email. So if you have any issues, some people have, some firewalls have blocked the link, etc. Just shoot me an email. That will also be included with the link. I think everyone has my email at this point. So we'll make sure that you get a copy of the presentation, the slides, as well as the recording. So with that, let me introduce Corinne, whom we are delighted to have join us today. She received her PhD in physical chemistry at the University of Bordeaux in France, and she did her postdoctoral work for Sanofi Bioindustries at Tulane University in their physics department. And she is currently working in Material and Analytical Sciences department as a senior scientist at Boehringer Ingelheim. She's based in Ridgefield, Connecticut, where she has 15 years of experience as a preformulation scientist. For the past couple of years, her focus has been on developing predictive biorelevant in vitro methodologies to understand in vivo performance of oral formulations, which is the topic of her presentation today. So with that, I turn it over to Corinne, and thank you so much again, Corinne, for joining us.
Thank you, Karen, for this introduction, and thank you for the opportunity of giving this presentation. So I'm trying to move my slide to the next slide. Okay. So as Karen mentioned, I work for Boehringer Ingelheim in pharmaceutical in the R&D site in Ridgefield, Connecticut. And I work in the preformulation group in the material and analytical science department. So preformulation is a group of studies that focus on the physical chemical properties of the new drug candidate that could affect the drug performance and the dosage, the development of a dosage form. So understanding those properties is important information for formulation design. So in our group, we are focusing on evaluating the physical chemical properties of our API that could have an impact on overall drug absorption. And our goal is to guide formulation design and development and accelerate clinical evaluation of medicine and reducing development time. So we are developing biopharmaceutical in vitro and in silico tools to identify the key factors that influence drug absorption. And by using those tools, we want to gain a good understanding of the rate-limiting steps to drug absorption so we can forecast in vitro performance of oral formulation, and we can influence preclinical and clinical studies. So we are involved in different stages of the drug development process. We can be involved as early as discovery to start of development, preclinical development, and clinical studies. And so how can preformulation guide formulation development? So we need to be able to guide formulation development, we need to have an understanding of oral drug absorption. And so drug absorption is a mass transport of drug molecule from the GI tract through the intestinal membrane. And I hope I I can show on this slide that drug absorption, overall drug absorption from the GI tract is a complex process. And it's a sequential process of dissolution and intestinal membrane permeation. So first, the drug particles need to dissolve in the GI media. Then the dissolved drug molecule diffuse through the aqueous boundary layer, and the unbound drug molecule permeate through the membrane. So the drug molecules that transfer through the membranes are the drugs that are available, the molecules that are available for absorption. So for our compound, most of our drugs have low solubility and are lipophilic, and often the dissolution will be the rate limiting step to absorption. The dissolution or the solubility, because the maximum amount of drug that dissolve will be limited by the drug solubility. And also the amount of drug crossing the membrane can be limited by the diffusion across the aqueous boundary layer. So often when people want to improve drug absorption, they focus on improving the drug concentration or increasing the dissolution rate. And so we have different formulation strategy that we can use to increase the dissolution rate or drug concentration. We can use particle size reduction, salt form, co-crystal. We can use different solubilization techniques by making micelles formation, complexation, or we can use supersaturating formulation like SEDS formulation or amorphous solid dispersion. And so, for example, in the case of amorphous solid dispersion are known to disintegrate very rapidly and reach a high drug concentration, much higher than the crystalline drug concentration. So this will increase the driving force to absorption. And in some cases, amorphous solid dispersion can disintegrate into drug-rich colloidal aggregates. And those aggregates can be very beneficial for in vivo performance. So in some cases, they can decrease the diffusional resistance across the aqueous boundary layer. And they also can act as rapidly diffusing shuttles of unbound drug. So that can continuously replenish the free drug in the GI tract as the drug is being absorbed through the membrane. So another example is complexation. So for example, complexation with cyclodextrin cyclodextrin is known to be can be a great solubilizer for API, but it can also reduce the drug permeability. So there is a trade-off between increase in solubility and decrease in permeability. So you can see that different excipients that we use in formulation are going to affect both the drug concentration and the permeability. And so if we only use a conventional dissolution methodology that compare the dissolution rate of different formulation and the extent of drug concentration, that can be misleading. So really to understand the mechanism of solubility enhancement from different formulation, it's important to look at the combination of the dissolution and the permeation. So for this, we're using dissolution and permeability chambers from Pion. And so this is with this equipment, we can measure in real time, we can monitor both the dissolution in the donor and the amount of drug that goes across the membrane, which is the drug that is directly available for absorption. Since, our assumption is the membrane is not permeable to the micelles or colloid or other bound drug species. So on this next slide, so I am showing on this slide the different tools that we're using in our group, in our pre-formulation group, and to drive formulation development. So early on, when we have a little bit, just a little information on the drug, we use GastroPlus modeling to give particle size target if milling is needed. And later on, when we have phase 1 in vivo data, we also use GastroPlus to do simulation using the in vivo data from phase 1 and in vitro dissolution to develop mechanistic in vivo and in vitro correlation. Another tool that is popular is the TinyTeam. So the tiny team is a dynamic in vitro gastrointestinal model that simulates the GI condition of human. And we're using the tiny team later on to support optimization of formulation of food effect prediction. And our latest addition in our tool from our toolbox is the Pion microflux or bioflux. And this instrument is similar to the smaller unit, the microflux. And so we are using fiber optic probes that are monitoring in real time the dissolution and the permeation. But with the microflux or the bioflux, we are using the USP dissolution apparatus, which is more biorelevant. And so I'm going to talk about the rainbow microdisc profiler and the microflux in the case study. So I'm not going to go over, but those are instruments that we use when we have a very small amount of drug available. So the first case study that I'm presenting, this is the first API that we use on the Pion microflux. So we had just received the instrument, and I was working on, I was supporting pharmacology and safety profiling studies. So we were working on developing a preclinical formulation for high dose safety study in rats. So this API is a BCS class 2 compound with low solubility, moderate permeability. And the pK was very low, so pK of 1.2. So we couldn't make any salt form. The formulation requirement and challenges, so we wanted to have enough sufficient exposure of the drug, and so we needed to enable formulation. And ideally, we wanted to predict trend in animal exposure and determine a dose range that would provide linearity of exposure. And the goal was to optimize the number of animal study. And the challenge was that, so the dose range was very wide, and we, for tox study, we wanted to push the dose to 750 milligram per kg. So it's very high dose. So we did some gastroplus simulation, and we saw that for higher dose, we were having a drop in absorption. So we tried different solubilization approaches. We tried solubilizer, cyclodextrin, surfactant, but those didn't provide enough solubility benefits. So we tried to reduce the particle size, and again, we didn't really see an advantage in terms of dissolution rate. There was aggregation forming. So our next steps was to look into supersaturating formulation. And so before making the amorphous solid dispersion, we wanted to know if the amorphous material, if we'll have gain advantage of using the amorphous form. So on this slide, I'm showing two different methodology that we use. So this is amorphous solubility on the left side, and on the right side, it's solvent shift method. And we're using those methodology to assess if we will have any benefit of making amorphous solid dispersion. So why do we want to make amorphous form? So amorphous form is energetic form that will have a higher solubility than the crystalline form. And so the amorphous solubility represents the maximum amount of free drug concentration that can be reached. So it's an important information for formulation development. So the methodology that I use to measure amorphous solubility has been described in the literature in the work of Lynn Taylor's group. And in this experiment, we use a small amount of crystalline material that we pre-dissolve in an organic solvent, and we add small aliquot of the dissolved drug. And we record the UV spectra after each addition. So to analyze the data, we look at the UV spectra at different angles. So here I'm showing that, so we look at the turbidity, and we look at the zero intercept method. And the zero intercept method, it's a feature of the OPPO software from Pion. And this method was presented during the Pion training course. And I had also many exchange And with Constantine, who has been helping me working on this methodology and data interpretation. And with discussion with Constantine and Oksana, they always, stress about we need to look at the data at different angles to get a full picture. And it will make sense at the next case study. But so here what we are seeing, so on the top graph, I'm showing the turbidity, which is the absorbance at the non-absorbing wavelengths. So when the compound dissolves, there is no absorbance of those at those wavelengths. But now if we form a second phase for example, the drug precipitate as a solid, or there is another liquid phase, then we should see an increase in turbidity. So, and in the zero-intercept method, we look at the point of zero-intercept of the second derivative spectra. And at those zero-intercept points, if the drug is fully dissolved as a monomer, the absorbance is going to stay at 0. But now if there is a change in the drug molecules, again, precipitation or another phase forming, we should see a shift at those zero-intercept points. So in both of those, in the turbidity, by looking at the turbidity and zero-intercept method, what we see is that we can dissolve the drug up to 150 microgram per ml before we see a shift in absorption. And so the concentration, the crystalline concentration of that drug in this media is 12 microgram per ml. But we are seeing that if we use the amorphous form, potentially we can really benefit from the concentration of the drug that will dissolve in the media. So on the right side, I'm showing the solvent shift method. And this methodology is telling us, give us information on the supersaturation, the maintenance of supersaturation. So if we induce supersaturation of the drug, is the drug going to stay supersaturated or precipitated? And so in the blue curve, the drug was pre-dissolved in an organic solvent and then added to passive media. And there is no polymer in that media. Now, on the red and orange curve, the drug is also pre-dissolved in organic solvent, and now it's added to passive media with some polymer. And we can see that, so when the drug is added in the media with no polymer, the drug stays supersaturated for about 20 minutes, but then it really precipitates out. And then when we add polymer in the media, we can maintain supersaturation for much longer time. So having this information now, we decided to make amorphous solid dispersion. So we spread wise some amorphous solid dispersion. And so as I mentioned earlier, this is the first API that I was using on the Pion. So I wanted to build up some confidence of the instrument, and I wanted to compare the regular dissolution that we are usually using with HPLC to the Pion microflux. And so on this graph, I'm showing, so what I did here is I dissolved the amorphous solid dispersion in passive media at different concentration, a different dose that correspond to the dose that were given to animals. And so I took a time point at 20 minutes, 1 hour, and 2 hours. And so here we are seeing the concentration as a function of the dose. And the solid lines are representing the total concentration of the drug. And then in here in the insert, it's I am representing the concentration of the filter samples. So all of the species that are in these samples are less than 0.2 micron. And so what we see, so first we can see that all the formulation dissolve at comparable concentration. And it's difficult to make any assessment on the performance of those formulations by just looking at the dissolution. But what was interesting is that, so what we see is that the concentration, the total drug concentration is much higher than the concentration of the filtered samples. So our assumption is that when we dissolve this amorphous solid dispersion in passive media, it's forming larger aggregates. And what I found interesting is that if we look at the filter samples who may be representing the concentration of the free drug, it's definitely representing the concentration of the smaller aggregates. We see that for the dose of 300 milligram per kg in rats, we see that we are reaching the highest concentration of small species. And this corresponds to 150 microgram per mil, which is what I showed on the previous slide, correspond to what we think the amorphous solubility. So now on the next slide, this is the results of the Pion microflux. So I used the same samples and I dissolved the amorphous solid dispersion at different concentration in the donor. And here I have represented the concentration as a function of time. So in the donor and in the acceptor chamber. And so at the time, again, like that was early on and it would take me time to set up this whole experiment. So I would let it run overnight. So this is why here I'm showing a recording up to 10 hours. So in the insert here, I'm showing different, the results of the dissolution for different doses. So again, you can see that it's difficult to make any to make any conclusion from the dissolution. What we saw is that there is every dose shows supersaturation, and then there is a sharp decrease in the drug concentration. So now in the flux, in the acceptor chamber, we would see an initial flux, a faster flux, and then a later flux. And so I I calculated both of those flux, the initial flux and the later flux, for each dose concentration. And so there was much more variability in the duplicate with the initial flux. So on the next slide, I'm showing the variation of the later flux. But you know, I think the variability can be explained in the initial flux. In the first hour, the formulation is dissolving, so there is effect of dissolution kinetics. So that may explain the variability. So on this slide, I am comparing the in vitro, the flux that we measured in the Pion on the in vitro setup, and then animal data. And so this is the variation of the flux as a function of dose. And so we made two amorphous solid dispersion or spread-wide dispersion because we couldn't like really dose at 500 milligram per kg. There was problem with syringeability, dosability. There was so much solid at that concentration. So the black dots are representing the spread-wide dispersion that we made with 30% of drug load, and the blue dots or the blue line are representing the results of the one-to-one solid dispersion, so 50% drug load. And also later on, we work with dispersal, and they made some kinetisol material. And I wanted I was curious to look at the flux data that we get with the kinetisol material. So I tested at 300 milligram per kg, and the results of the kinetisol flux are really overlaying with the amorphous solid dispersion. And the kinetisol is a much better material to work with than the spread-wide dispersion. It's much denser, and it was much easier to work with. But so I think what was useful in this case is that we can see that there is, from the in vitro data, you can see that there is dose linearity where the flux is increasing up to 300 milligram per kg, and then it stopped increasing. And we see the same trends in vivo rat data. So I thought that was pretty successful useful use of the microflux. So now in this second case study, so I was this, so we used a microflux setup to support formulation selection, and that was for rat studies. So in this work, so when we got the API early on again, and we had limited information on that drug, And there was an issue. So the solid form was about to be selected for development, but there was an issue with the solid form that was about to be selected. So we wanted to see quickly if we could switch form. And we had animal study available. So we wanted to try different form and see the in vivo performance. So this is a BCS class 2 drug with low solubility, moderate permeability, and a weak base. And so for this API, the concentration in the stomach environment was much higher than in intestinal environment. So we were thinking that this drug, upon transfer from the stomach to the intestine, could precipitate out fast. And so we had a limited amount of time and to select the formulation for a rat study. So we looked at everything. We looked at the pH effect. We looked at particle size reduction. So we had 2 or 3 different solid forms to test. And we looked at amorphous solid dispersion. And at the time, because it was we were making formulation for rat studies, we thought that we should look at the performance of those different form of formulation using a 2-step dissolution media that is, mimic the rat physiology. So we started dissolution in pH 4, and then after 30 minutes, we changed to pH 6.5. And so what we saw, and here I'm only representing 3 of the dose that 3 of the drugs that it's 1 drug, 3 of the formulation. But so this is the black trace shows the dissolution of the unmeal. The jet meal is above it, and then we saw that the amorphous solid dispersion was showing a significant increase in drug concentration. And everything else that we tested was between the jet meal and the unmeal material. But so then we did a rat study, and when we got the result, we saw that everything was very similar to each other. So there was not a huge improvement of the amorphous solid dispersion. So afterwards, we went back to this drug and tried to understand. And that was the second API that I tested on the Pion. So I wanted to see if I could use the Pion technology to understand what has happened. So here again, I'm showing, this is the amorphous solubility measurement. And so as I mentioned before, we look at the spectra at different angles. And so we look at the turbidity or the absorbance of non-absorbing wavelengths. We look at the ZIM methodology, and we also look at the area under the curve second derivative, which is our standard curve. So when we add the drug in solution and the drug dissolves, the concentration should increase linearly with drug addition to a certain maximum concentration. And then, after this maximum is reached, if sometimes the drug precipitates in the media and we can see that the concentration is going to 0, is decreasing to 0, or in this case, it looks like it's precipitating, but it's still holding a certain concentration. So we think that the drug precipitates into amorphous particles and it stays at the amorphous concentration. So by looking at the area under the curve and the turbidity, we see that we can dissolve this drug as a monomer up to a concentration about 140 micrograms per mil. But now if we look at the ZIM plot, it shows that by addition of the drug up to 50 micrograms per mil, there was no change in the spectra, which is expected if the drug is dissolving. But then after 50 micrograms per mil, there is an increase, a linear increase with each addition of stock solution. So our interpretation is that a new phase is forming, and that has a different UV absorbing properties. So we see a shift in the spectra, and we see that a linear increase of the API in this new phase. And in here, I'm showing the Z methodology, but in this case, I added some polymer in the passive media. And again, what we see is that, it seems like the amorphous solubility is at 50 microgram per mil. And then the second phase that is forming could be a liquid phase separation is holding for a little longer. So from this information, we had information that we think that the amorphous solubility of this API is at 50 microgram per mil, which is very close to the crystalline solubility. So doesn't look like there is a big advantage of using amorphous form. So on this slide, I just wanted to compare. Those are 3 different methodologies that I use. So the solvent shift methodology we usually use to assess the drug precipitation tendency or supersaturation tendency and to rank order different polymers. So in this case, once the drug is introduced in the media at high concentration, it immediately precipitates. So the red curve, in the red curve, there is no polymer in the passive media. And the concentration at the end after 2 hours corresponds to about 50 microgram per mil. So it looks like drug precipitates in the amorphous form. But if we had a polymer in the passive media, then it can help supersaturating the drug. And so because this API there is a stiff solubility profile on this API, the drug concentration in AGF is much higher than in passive media. So we wanted to assess the precipitation inhibition of polymers using a 2-step gastric methodology that is more biorelevant. And in this methodology, we also dissolve the drug in an organic solvent and we add the drug to AGF. And after half an hour, we change the media to passive media. And again, so what we are also seeing is that the drug completely dissolves in AGF and then precipitate out after transfer to the second media. And again, when we add the drug directly to the passive media with no polymer, the concentration that we reach is about 50 microgram per mil. And now this last methodology, so usually when we use the 2-step gastric, we are trying to mimic the behavior of a amorphous solid dispersion without making the material. So our assumption is that in amorphous solid dispersion, the drug dissolves rapidly in the media. So in the 2-step gastric, what we are doing is we are dissolving the drug and the polymer together in the organic media and adding and look at the concentration. And so I wanted to see if we actually use the real material, the amorphous solid dispersion, and we use a 2-step dissolution, how those 2 methodologies will compare. So here I'm dissolving the amorphous solid dispersion, and I did a 2-step dissolution starting with AGF, ending in SIF, and the results were very comparable. So on the next slide, so on this slide, I used the microflux, and here I'm showing the concentration in the donor of amorphous solid dispersion. And so this is an overlay of 3 different experiments. So on the first curve, I dissolved the amorphous solid dispersion in passive media, which has 0.2% SIF. And then on the red curve, I increased the concentration of SIF powder in the media to increase the concentration of bisalts and lecithin to increase the amount of mixed micelles in the media and increase the solubilization capacity of the drug. And what we see is that from going from 0.2% to 2%, we really increase the solubilization capacity of the drug by increasing those micelles. And the total concentration is much higher for the 2% SIF. But if we look at the flux results, so this is the results, the flux measure in the acceptor chamber. And what I'm showing here is the relative flux. So these lines correspond to the flux of the unmilled material. And this is the jet mill the flux of the jet mill material normalized to the unmill. And this is the flux of the amorphous solid dispersion dissolved in 0.2% SIF. And by increasing the drug concentration of the micelle bonds concentration from 0.2 to 0.5 to 2, what we see is that even though we see a large increase in concentration, the flux is not increasing and actually seems to decrease slightly. So now going back to our in vivo data, so this is the flux that I measured in the microflux of the amorphous solid spread-wide solid dispersion, the jet mill material. And by comparing the flux ratio between the SDD and the jet mill material, we got like very close. I mean, we got similar results than the in vivo data, that data. So that was, again, that was a good experiment to rank order the formulation, rank order in vivo formulation performance in rat species. So our conclusion is that really a well-designed in vitro assay can be done in early stage development with very small amount of material and can provide very valuable insight for overall formulation development. So the dissolution and permeation assay are a critical tool that we have in our toolbox, and that is helping us in getting fundamental knowledge of rate-limiting steps of drug absorption and dry formulation development decision. And so I would like to thank and acknowledge my Boehringer Ingelheim colleagues from Preformulation group and my colleagues who have been helping me working on those drug development, the case study that I presented, and colleagues from the biopharmaceutical group from BI in the US side, Germany and Japan. And I also would like to thank the Pion, you know, I want to call them Pion colleague because over the past few years, I had so many interaction with people from the Pion team that I really think of them as colleagues. But I have met many people from Pion, and everybody's been very helpful, very knowledgeable, and always very responsive when I contacted them for different issues for the instrument. So everybody is always available. So that's, I think it's a strength of the Pion team, the people who are working for the company. And I especially would like to acknowledge and thank Constantine. He has been so helpful to me throughout the years since we got the instrument. He has really been a great help and provided great directions and has been helping us in data interpretation and understanding how the Pion tools can be used in developing our API. And it was always such a great pleasure to go to a meeting, to APS or another meeting, and talk to Constantine and meet him. And I'm very lucky, I feel very lucky that at the end of last year in October, Pion had a great meeting in Boston, bio-relevant meeting. And I'm very lucky that, I feel very lucky that I got to spend time with Constantine and Oksana. And I added the absolutely cylindrical man picture here. I don't know, every time I have attended a presentation from Constantine, he's never failed to introduce the absolutely cylindrical man, and I always really like that. So thank you.
Thank you so much, Corinne. You're gonna make me cry. That was so nice. Your words about Constantine. So thank you from all of us.
Yeah, I don't have like the dancing video like Ocean presented at the first webinar, so that's too bad, but yeah.
He is truly, truly, truly missed. So thank you for your kind words. I do see that we have quite a few questions that have come in. So I think with that, I will turn it over to Carl and the group of panelists that are going to ask and answer some of the questions that have been coming throughout your presentation, Corinne.
Yeah, thank you, Karen. Thank you, Corinne, for the interesting presentation. I'm going to try to moderate the question and answer session. So I have a question here for you, Corinne. In the microflux studies, how do you select your optimal dosing ranges for the tests if you want to simulate rat absorption? Is it scaled, for example, to the donor volume in the flux cell?
Yes, yes. So we try to, yes. So we scale down to the rat volume, exactly. That's what we do. And then we use this concentration to calculate the dose the concentration that we will use in the microflux.
Okay, thank you. So there seems to be a specific question about, I think, your second case study, which was, do you have any explanation why polymer 2 appears so different between the solvent shift and the two-step?
Oh, yes, absolutely. Yeah, absolutely. So, so this is what you mean, right? Why is there such a difference in supersaturating power between those two experiments? Is it what you mean, between the solvent shift and the two-step?
Yes, exactly.
Yeah. So this is the solvent shift, we use it to rank order the different polymers. But the way we set up this, the short answer is the ratio of polymer. There is much more polymer in this setup than in this one. So here we dissolve the drug to the polymer at 1-to-1 ratio. And in here we have like, we use 10% polymer in the media, which correspond to a 1-to-10 ratio. And so, of course, depending on how much polymer we are going to prevent more or less supersaturation. But we're not trying to target, how much benefit we can get. It's more for a rank order. And I think that the 1-to-1 ratio drug polymer will be more representative of in vivo.
Okay, thank you. So I have a question here, I think, for Naveen, who's also on the panel. So what BCS classification are the APIs that you are trying to formulate? And have you tried to formulate BCS classification for compounds?
Yes, I answered that question. Yes, we do work with BCS class 4 as well. And the second part of the question was whether we use some permeation enhancer. Sometimes in the formulation, if we do use surfactants, and that may have permeation enhancement capability as well.
Okay, thank you. Okay, here's a question. Perhaps Blint, you can take this one. So can you use the flux setup with CACO2 cells?
Yes, so currently the microflux or the macrobioflux systems are not, so yeah, we don't have too much experience with that. We know about a group who has tried that, but we ourselves don't have experience with cell assays.
So Corinne, here's another question for you. On slide 10, you've shown the flux from different formulations. Have you tried to use both early and late flux to make conclusions?
Yes, absolutely. So I look at, again, that was the first time we were using the instrument. And so I look at the variation of the initial flux and the late flux, and there was more variability in the initial flux on the replicate. But, after having the whole story and looking back at the initial flux, we also saw the same trend. We saw linearity up to 300 milligram per kg, and then the flux was decreasing.
Okay, thank you. Here's a related question. Perhaps I can take this one. Is the absorption rate a constant for a given drug using the microflux system? Well, the membrane we use in our flux setup is a phospholipid-based membrane, and permeability data has been shown to correlate directly to human jejunal intestinal permeability. But the flux itself depends on the dynamic events in the dissolution vessel. If the donor concentration in the dissolution vessel is constant, then flux should be constant. If it is changing over time, then it means that something is happening in the donor compartment. It's likely that the drug is supersaturating or precipitating, Also, you have to remember that it should only be freely dissolved drug that can permeate across the membrane. So any drug aggregates, precipitates, colloidal or micellar-bound species will not be able to permeate through the membrane, although in some instances they might provide a reservoir of drug that can replenish permeated drug. And so this can aid the kind of formulation effect of some of these, amorphous solid dispersions, for example, that may end up inducing liquid-liquid phase separation. So there's a question here about I think the KSD for rat dosing. It says, do you pre-suspend the ASD solid in some kind of aqueous vehicle, then dispense into dissolution vessel? And was your 1:2 API polymer easier to suspend than the 1:1 ratio?
So the first question about the KSD, I mean, I just added the KSD in passive media. And, but, I have done some different studies where I make a dose formulation and I add that dose formulation to the media. So it can go either way. I'm not sure I understood the second part of your question.
I think it was a question about how easy they were to suspend. Was the 1:2 drug to polymer easier to suspend than the 1:1 ratio?
Yeah. So the spread wide material, I mean, the KSD were like amazing because they are like dense and small particles, and it was so easy. And the dosability was great. And also, I forgot to mention, we also did later on some animal studies, and we had exactly the same in vivo absorption from the KSD and the spread wide solid dispersion. But so the 30% drug load, amorphous solid dispersion had much more polymer than the 50%, and it was so much solid that but so the 500 milligram per kg, I didn't even try to disperse that one. So that's why we made the 1:1 material was much easier to dissolve at higher dose.
Okay, thank you. Perhaps I can direct a question to Belint again. So several questions around membranes. It says, how important is membrane selection, and is the membrane coating stable in the presence of formulation excipients?
So membrane selection is important. Quite a few groups are using size exclusion membranes. Pion's current preferred method is a lipophilic membrane. We think it has an advantage, especially for BCS class 2 drugs. However, for a few low permeable compounds, the size exclusion membrane can have some advantage. In terms of the stability, obviously it depends on the properties of the excipients. Polymers are usually quite inert and don't damage the membrane. If you have a high concentration of of a strong surfactant, then there is a chance that gonna slowly damage the membrane. We have studies where we just see an unexpected big increase in the flux after 8 or 10 hours or 12 hours. That usually means that the membrane got damaged and there is a free diffusion or like direct channels to the receiver chamber. The good thing is that this is usually quite obvious in the assay. So if you see a dramatic flux increase with no obvious reason in the donor side, then that's usually an indication of a membrane issue.
Okay, thank you, Belint. So maybe another question here for Corinne. It said in one of the last slides on the second case study, you showed that the flux remained constant even when the apparent concentration was higher. Could you explain this again, please?
Oh, yeah, so you want, yes. So why do we see an increase in drug concentration in the dissolution, but it's not we don't see it in the flux, right? Is it what the question? Is
Yes,
it the question?
yes.
Yes. So what we think is that by increasing the amount of bisalts and lecithin in the media were increasing the formation of micelles. And the drug is bound in the micelle. And it's not, so with increasing the micelles concentration, we're increasing the amount of drug bound to the micelles. And so it decreased the amount of free drug available for absorption. I mean, we didn't look at to see if, but if you look at the flux, it looks like it's decreasing. So it's probably we're decreasing the amount of free drug in the media that is available for absorption because the drug is tightly bound in the micelles.
Okay, thank you. I can add a comment to that. I think there's quite a lot of publications on the topic of the solubility permeability interplay. So if you look up publications by Eric Dahan and Jonathan Miller, they describe that some formulations, although they provide enhanced solubility, it doesn't necessarily lead to enhanced permeability because the drug is bound and there is the free drug concentration hasn't been enhanced. So there's another question here. How do you know that nanoparticles or small colloidal droplets will not be able to get through the membrane if they are smaller than the filter pore size, which I understand is 0.45 microns on the filter support? So I can take that question. So we don't believe nanoparticles will get through the membrane. The filter support is coated with a phospholipid dodecane mixture. The filters become completely translucent, indicating that there's a membrane coating across the entire membrane, so it creates a barrier function. So we don't think nanoparticles should get across that membrane. However, we have done some flux studies. We have shown in some instances some evidence that nano-sized particles may have a higher flux than expected when compared to larger particle preparations. But we think this might be explained by the particle drift theory. There's a publication by Sugano which explains the particle drift theory. This suggests that very small particles are able to diffuse into the unstirred water layer or aqueous boundary layer close to the membrane surface, and then are able to dissolve directly across the membrane. So I think we're getting to the end now, so I'll just take one last question, and then I'll hand back to Karen. So are we, perhaps this is a question for Berlin, are we planning to have a webinar on the bioflux technology in the near future? And how can we use these types of apparatus to study bioequivalence?
So in this webinar series, we have started with a macroflux webinar by Hao Tian, and that was showing a lot of examples on bioequivalence prediction. It was showing our own data, also the data by a university that is our collaboration partner, and also a bunch of data from the Chinese FDA and how they are trying to predict bioequivalence, or actually considering to replace bioequivalence studies with flux studies. So I think that webinar is recorded and can be found on our website. So bioflux webinar at this point would not be that much different because we were showing both bioflux and macroflux data.
Okay, thank you, Berlin. So just to wrap up, this is the 8th webinar in a series that Pion's been running. So all of those webinars should be available from download from our website, or you can just send us an email and request the links to the series of 8 webinars. I'd like to thank Corinne again and all the people from Boehringer that have participated and helped in this presentation. I'm going to hand back to Karen now just to finish off.
Thanks, Carl. Yes, I just wanted to echo Carl's words as well. Thank you to both Carl and Bülent for being part of the panel, and of course to Naveen and obviously Corinne. We really appreciate you both being part of the Pion team also, so thank you. Again, I want to thank everyone for attending, and you will receive a link to the recording, and if you have any issues at all, your Pion representative is also going to get in touch with you just to make sure you were able to get the download, as well as send you the Q&A in a written format. So if you have any questions, just feel free to reach out to us at any time. Thank you again, and have a great day. Thanks so much.
Thank you.